Okay, so welcome back. You also kept quiet, so strange. I think I figured out the reason though. Like on my roster now, I'm seeing that like the majority of you are lower freshmen. So, seems like a lot of you are just straight out of high school or something like that. So, you're all just college. Can I go to the bathroom? You have to ask me to go to the bathroom and all that. No. In college now you're adults, so chillax. You can mingle and just don't need to be afraid. No one's gonna bully you anymore, no one's gonna stick your head in the toilets anymore, it's fine. You're safe. Okay. So yesterday we ended with a quiz, as you might remember. Yeah, that was like after quiz. I'm kidding. It was like a diagnostic, sort of for you to know sort of where you are, sort of hopefully jog your memory and whatnot, and sort of see where your mistakes were. So yeah, I haven't graded that yet, of course, because it was just yesterday.
Is that being counted to our final grade?
No, it's a diagnostic, that's why. Diagnostics don't count, right? It's just...
What? You could have said that.
What?
You totally scared us.
Yeah, but if I said it wouldn't count, you wouldn't have tried, right?
You would have
You would have left early and didn't know. You wouldn't have tried. Okay, so was a diagnostic just to see where you are from both of us, to see where you are, so you can see your mistakes. On Tuesday, I will give you another quiz on the same material, algebra and pre-calc, right? So stuff that came before, and that will count to your grade.
The same.
You have
Does
another?
that answer my question?
Okay. Yes. So I need to make sure you guys understand algebra and pre-calc.
There was it again? I didn't catch it. What day do you call it?
Tuesday. Next week. Tuesday coming. Yes.
Will the quiz be as long?
No, it'll be short.
Okay.
But it'll cover the same sort of material. On Friday, you'll have your first calculus quiz, right? So anything I teach in this class up until the Thursday will be on Friday's quiz. Yes?
Are all of your quizzes cumulative? Like
No, my quizzes sort of just cover
just like
piece by piece, right? So quizzes and tests, they're piece by piece. The only cumulative thing in this class is the final. And obviously, if anything really depends on anything, you should know. So, yeah, so that's that. So remember that. So the quiz we took yesterday, diagnostic. There's homework on the same material, by the way, already on WebAssign. I don't know if anyone did the WebAssign thing. But there's also WebAssign homework on algebra and pre-calc that's also due on Tuesday by 4 o'clock. So make sure you get the WebAssign info. So yeah, Tuesday another quiz. We'll continue with calculus. Thursday we'll continue with calculus. Friday we'll go calculus quiz. Okay, that's the basic agenda for next week. And we're just going to now go through all the material starting in the order that I have it in the syllabus. So we're starting on chapter 1. We're going to start with section 1.1 and then move on to 1.2 and so on and so forth. 1.1 and 1.2 is also sort of algebra and pre-calc, especially if you did algebra and pre-calc here at City College. You would already know everything I'm going to talk about in 1.1 and 1.2. So you might be a little bit bored, but it's very important foundations for you to know. I need to make sure you know some of these things. So, we're just going to go through them. Most of it should be familiar. It's sort of a lot to write down. Don't know if I want to write it down. I guess I'll sort of feel it out, see how the classes follow me, and then I'll decide if I can skip anything or write anything down. So let's jump into it. Section 1.1. We're going to talk about functions and their representation. Can anyone tell me what a function is? Yeah?
When a quantity depends on, when something depends on something, like, but it's like in those words about quantity though. When a quantity changes, when it depends on something.
Yeah, sure, they arise when we try to model quantities in Calc 1 and 2, we'll talk about single variable functions, which means Calc 1 and 2, you do single variable functions. Which means you have one quantity depending on one other quantity. Sure, yeah, so that's just a reminder of that. But what is like a working mathematical definition for a function?
It's like a set of like 2 points where you put one in and then it only gives you one result.
Right, so that is a very sort of specific answer. We can tidy that up. A function is a rule that assigns to each element in a set exactly one element in another set. Right? So a function is just a way that we assign values to things. So if I know one quantity, right, so we can say input, or call the independent variable, these are elements in the domain. Right? So we can say something's an input, like X is your input, Y is your output. There's also something called a range, which is just a set of elements that you map to, and outputs or dependent variables are just elements of the range. So basically a function just, it's a rule from which you have one set called a domain, and there are guys living in here. And there are other guys living in here. This is called a codomain. And then there's a rule that says you are assigned to this guy, you are assigned to that guy, you are assigned to that guy, you are assigned to that guy. This set here of guys that are assigned, that we call the range. Right? So a function is just a rule that you make assignments with, and you say the variables, this set here has elements that depend on what value you pick. This guy gets picked depending on if this was your input or that was your input. Right? Notation. We say y equals f of x to mean there is a function called is the name of the function. It takes input variables where the generic ones are denoted by x and gives output denoted by 1. Okay, so simple example. I'm not saying anything strange, right? Like everyone has seen functions before. So let's say I have function f of x equals x plus 2. Right? So, and let's say my domain is the set of real numbers, right? Like or integers. So my codomain is also the real numbers, right? So I can have the number 1 and the number 2 and the number 7 and the number 9, right? So under my function f, 1 would go to 3, right? Because you just, this rule says when your input is x, what you do to it is you add 2. It gives you a rule to get an output, right? So this would go to 3, this guy would go to, we're adding 2, so that goes to 4, this guy would go to 9, this guy would go to 11, and so on and so forth, right? So this just tells you a rule of what you're going to do to certain input values to get an output value. And notice that each input value has only one possible output value, right? 1 can only map to 3 if this is the rule you're using, right? Because if you had 2 to 1, the only thing you can get is 3, right? So that's an example of a function. So, by the way, the above diagram is called the mapping diagram. And it's sort of easy to tell which kind of mappings are functions. So if you have a mapping diagram that looks sort of like here, like that's a function. That's a function. This, by the way, is called a one-to-one function. Right? Because as you can see, each input has its own unique output, and no other guy has that one. It's just 1 goes to 1, and no one else goes to that one. This is called a many-to-one function. Right? It means that each input has one output, however, many things can have the same output. Right? So here I see 2 guys going to the same output. Right? It's still a function, but it's called a many-to-one function. Can anyone give me an example of a one-to-one function? Yeah? Oh. Yeah, I gave you one, right? So example here would be f of x equals x plus 2 is a one-to-one function, right? How do you do a many-to-one function? An example of that? X squared would be a many-to-one function, right? Because -1 and 1, for example, go to the same thing. A positive value and a negative value. So this could be -1 and that could be -1. They'll actually both go to 1, right? That's called a many-to-one function. Things that are not functions are things that of that sort. Notice here, this input value has two output values. It doesn't have exactly one output value, right? So this is not a function. Can anyone tell me something that's not a function? Huh? Hmm? You mean like absolute value of x? That you mean? No, that's a function. It's a many-to-one function. Yeah?
Y equals radical x, the whole thing.
Nope, that's also a function.
Why?
Y equals 2 is also a function.
X to the third.
X to the third is also a function.
X equals 3.
Also a function. Also a function. Yeah, doesn't exist. Doesn't. He wasn't here yesterday, so it's fine. Yeah, divine by zero classroom. Don't talk about those things. Also a function.
Maybe x squared.
Nope. Also a function. Come on, you guys study things that were functions in math, right?
A circle.
A circle is a very good example of something that's not a function that everyone should be familiar with. Circle, something like x squared plus y squared equals 1 or 7 or whatever, right? Because notice you have an x value that gives you two different output values, right? So a circle is an example of a relation that is not a function.
Oh,
Right?
parallel line.
Huh?
Parallel line equals not a function.
Well, you could really think that a parallel line is really a single thing. It's sort of two things. But lines are functions.
Yeah, line is.
Right. Pretty much anything that you can write like this will be a function. If you can say y equals and you describe something with only x's in it, it's going to be a function. Right?
We could have said negative absolute x.
No, it's still a function.
Maybe it was sideways.
No, it will flip upside down. We're going to talk about that in the next section also. Okay. So, you guys obviously know about functions, just don't know about things that are not functions, but okay. What else do we talk about? Come on, guys, get a picture. Okay, other ways to represent functions. So we've seen one mapping diagram was a visual way of representing a function. But there are other ways you can do it. Things like table of values. Right? So I could literally describe, for example, if I want to describe that function, I could literally just have a table of values, right? Where I say y equals f of x, I can put x values here and then I can repeat the y's, right? So if I have -1, this value would be, I'm adding 2, right? So this value would be 1, if I have 0, I have 2, if I have 1, I have 3, if I have 7, I have 9, etc., right? You can list them as a table, right? You can also do coordinates. So again, if I want to talk about this function, x plus 2, I could have said that f equals the set of, and I can again do it sort of like a list. Another very important way to do a function is by doing graphs. Huh?
You don't have to put the x on the second. F of
No.
x.
Right? That is called. Right, so you can do mapping diagrams, you can do tables, you can do sets of coordinates, and you can do graph, a very famous way of representing functions. So if I had f of x equals x plus 2, what would that look like?
Going to off and
So the y-intercept is 2, and it goes like this, right?
No.
Straight. Goes like this, straight.
No, the other side.
How does it look?
It goes back.
It goes like that.
Yeah.
And one way to do this is to, you can literally like plot points, right? So you know that if you plug in 0, the output is 2. If I plug in 1, the output would be 3. You know, if I plug in 7, the output is 9, and so on and so forth. But plotting is like middle school. No one plots points anymore, right? We're going to learn how to draw functions by knowing about basic shapes and then transforming them. Right? So. Let's go back to domains. So remember the domain. Is a set of possible inputs that we could put a restriction on, but we don't always, right? So that's just a domain. Anything that we can plug into the function and it works, we say that that element is in the domain. So, for example, what's the domain of that? All real numbers. So here we can say the domain of f is, many ways we can write this. We can say all real x. We could say something like minus infinity to infinity, right? We can say just like r. Right? There are many ways to say that something is a domain. Right? This is in words. This is using what we call interval notation. This is just a symbol for all the real numbers. Suppose f of x equals 1 over x. What is the domain of that?
Except
All real numbers except 0. All real x except x equals 0. Or could you write that in interval notation?
Yeah, so you write parentheses 0. No.
Union. Or you can write that. You can say something like, you can write as a set all real numbers such that x is not equal to 0. You can also write that. Many ways you can write. Typically, we'll ask you for the interval notation, but knowing the domain of your function is going to be important. We'll see that later. You need to know how to find the domains. Suppose f of x equals radical x. What's the domain?
All constant.
All real x such that, what's the restriction on x? Greater than or equal to 0. What about By the way, how would I write this in interval notation? Zero and infinity, sure, yeah, like that.
Yeah, bracket.
Use brackets on the guy that's included, right?
Square bracket.
Since it could be equal to 0, you write that sort of bracket. Okay. In general, something you should be aware of, if your f of x is equal to some sort of root of x where n is positive integer, then the domain of f is 0 to infinity if your n is everything if n is, what are these in the blank? Fill in the blank. This is my function and can be any positive integer. When is the domain this and when is it that? When is this true? Yeah?
With the even.
When n is even. This is when n is odd, right? Even means like 0 plus 0, 2, 4, 6, 8. Well, it includes the negative of these, but here I'm saying this is positive. And odd is, of course, like 1, 3, 5, 7. Right? So if you have an odd number here, domain is everything. If an even number there, the domain has to be positives. Or if I say what's the domain?
Plus or minus.
The domain is plus or minus 2.
And means plus or minus 2.
Yeah.
Okay, how do you know?
You can have it zero.
Right. One way is so you can factor this difference of two squares, and this is blah. So we know denominator cannot be 0.
So it can't be.
And x minus 2 equals x times x plus 2 equals 0 if x is 2 or minus 2. Therefore, the domain of f is infinity minus 2. How would I think this? Tell me the complete answer.
Union.
Union.
Union 2.
How about that one? What's the domain?
It's the same, right?
X can't be 2.
Sure, but so you're saying means the answer is the same as that?
No, and it can be.
It's only positive.
Can be
Negative infinity bracket.
Okay, so here,
It can be negative 2 or 0.
here we have two restrictions, right? One, there's a radical.
So it can be negative.
So we know that 1, we need that x squared minus 4 to be greater than or equal to 0, right? Because of the radical. And 2, we need that x squared minus 4 is not equal to 0 because of it's in the denominator, right? Now, how do I make sure that this is true?
It has to be greater than -4.
Solve for plus x for x.
Yeah, how would you solve for x? X would have to be what? How do you solve this? Okay, so you start with x plus 2, x minus 2, greater than 0, then what?
2.
X is greater than +2 and x is smaller than 3.
How do you know?
It's greater than 0, so it's positive.
So you said when equal to 0, the solutions would be what? X would be minus 2 and x is 2, right? So you can do a number line, minus 2 and 2, and then you just test the intervals, right? So you put in a number over here, like try minus 3, right? Plug in minus 3 here. This would be a negative, that would be a negative, negative times negative,
Positive.
positive works. So that works. Put a number over here, like 0. This would be 2 times minus 2, that's less than 0, so this does not work. Put a number over here, like 3. Right? This would be positive, this would be positive, positive, positive is positive, so that works. So this one works everywhere here. Right? Including here, but we're going to get rid of that to over here. This one works everywhere, except at those two values. Right? Now what we're looking for is the overlap. Right? Now where do they overlap? Right?
Towards negative.
So this is for x squared minus 4 not equal to 0, and the one for x squared minus 4 greater than or equal to 0 looks like that. Where do they overlap?
When positive is going and towards
Over
negative.
here, right? Once you're strictly less than -2, and once you're strictly bigger than 2. Right? So in this case, the domain
Is -2 to -2.
so here the domain effect is from minus infinity to minus 2, not including minus 2 because that would make it 0, union
2 to
2 to
infinity.
infinity. Right? Because otherwise things won't work. What else do I want to talk about? Do we know what the range is?
All possible solutions.
Okay, the set of possible outputs, right? So you domain is talking about the set of possible inputs. The range would be the set of corresponding outputs. So that's you define the domain and the range of, say, x squared x cubed you get nice problems in that. Okay, so x squared plus the domain. possible values you can plug into x squared?
All real numbers.
All real numbers, anything. You can take any number and square it. There's nothing that will stop you from doing that. What is the range?
0 and above.
0 and above. Probably the easiest way to see this is from the graph. Y equals x squared looks like that. Right? So if you look at the horizontal things that you can plug in, that tells you the domain. The vertical things that are outputs tells you the range. Notice here all y values from 0 and above are accounted for. Right? While all x values are accounted for in general. Right? So how you know is basically if you can travel to the graph, it's in the range by a horizontal motion. Right? So if your y is 0, you're on the graph. If your y is 1, it's possible to hit the graph. If your y is negative 1, you go to the left, you go to the right, there's no graph. It's not in the range. Right? X, you can always, by vertically moving, hit the graph, no matter how far along the line you are, and anywhere you'll be able to hit the graph. So the domain is everything. This one, what does y equals x cubed look like?
Yeah, a line.
Switch. Okay. So what's the domain and range?
All real numbers for domain.
All real numbers for both. Right? Because no matter where you go on the y, you would always be able to hit the function eventually. Right? Same thing for the x. Right? And this, we're going to talk about this later, but this works in general. If your powers are, if you have x to an even integer, then this will be true, even positive integer. And if you have an odd one, this will be true. What about radical x? What does radical x look like?
It's 0 to
The graph.
the graph would be
Oh,
like
okay.
this.
Right.
Yeah.
Looks like this. The 0 is included, and it has a graph.
Yeah.
Right? And it keeps going forever. It keeps rising, but it rises at a slower rate as you go on. Domain,
All positive.
range,
Square bracket 0 to infinity.
range, same. This is familiar, right? Like you guys have seen this all before?
Yeah.
Okay. Something else I want to talk about. One way you can recognize a function that you should know is the vertical line test. Let's talk about that. Way to recognize any vertical line will cross graph of this is the test. How many times?
One.
At most once. Right? If it ever does it more than once, it's not a function. Because it means you have two outputs corresponding to one input. So example, functions x squared again. Right? Any vertical line I draw, we'll cut it at most once. Right? This is y equals x squared. That is y equals radical x. Again, any vertical line, cutting at most once. It's possible to draw one that touches it 0 times. That's why I have at most. So again, go to a circle. Here, vertical line touches it twice. This is x squared plus y squared. Or any random function that does anything. Right? So if you're plotting something and it looks, a vertical line will touch it more than one time, it's not a function. As long as you touch it only at most one time, it's a function. It's called the vertical line test. Someone mentioned this earlier, but we're going to be using it sometimes. The function absolute value x.
It's a V shape.
It is a V shape, that is correct. What's the mathematical definition?
It's always positive.
It's like a straight line. Straight line.
It's always positive.
Huh?
It's always positive.
Yeah, give me a formula. A rule that defines it. Let's illustrate it. Let's say I want to take the absolute value of -2, the absolute value of 4, absolute value of 5, absolute value of -7.
7.
What's this?
2.
This?
4.
This?
5.
This?
7.
What do you notice?
Maybe
It's 7.
Right, 4 didn't change. Pi didn't change. Why? They were positive.
Positive.
When it was negative, what happened?
Turn positive.
We changed the sign. This is x if x is greater than or equal to 0, and minus x if x is less than 0. Right? If it's positive, don't do anything. If it's negative, change the sign. Right? This gives you a definition. And I wrote down this thing, which I hope you guys understand. It's a piecewise function.
Oh, yeah.
This is another important concept. This occurs when the function's definition changes based on what region of the domain you work in. Right? So you call that piecewise function, where the definition will change depending on where you are. So for example, in the case of the absolute value function, if you're on the right side of the y-axis, the definition is different from if you're on the left side of the y-axis. Right? We call it a piecewise function. Another example of a piecewise function. Something like x equals x. X is greater than 2. And I can let it be 2 if x is less than 2. How do you graph this function?
You find 2 on the graph, and then you notice that has to be less.
Do we know what each of these look like separately? Y equals x and y equals 2. What do they look like? What does y equals x look like?
And lines.
Straight line, diagonal, cutting through the origin at 45 degrees. This is just a horizontal line going through 2, right? So first thing, if you're graphing things, a piecewise function, you have to know how to graph all the pieces independently, right? Now basically what this is saying is that this is the definition when you're in this region, as long as you're to the right of 2. If you're at 2 or less, this is the definition. So that sort of tells you that here, if you're at 2, that's the part of the function you want. You sort of ignore this part. And then this one says if you're at 2, this is the part of the function you want. You ignore that one, right? Because you don't, this only works when you're less than or equal to 2. If you're greater than, you don't care, you're something else. This works if you're greater than 2. And so what you do is you sort of ignore pieces of the graph and then you put them on the same picture, right? So one way you can do it is you know in your head what y equals x is like. So the point that you're breaking up at, like at 2, you start to plot it at that point. Now when your x is 2, what does y equals x give you? Well, it would also be 2 here, right? Open circle, and we know that it goes like this. Right? Now for the other one, we know it's just a horizontal line going through 2, and we fill this in because this can be equal. So that's an example. I'll end with one more definition of a piecewise function. Well, example. That's obviously piecewise, right? But it's not a function. How do I know? It doesn't pass the vertical line test. So something like this could be y equals x if x is greater than or equal to 2, and it's equal to 1 if x is less than 3. So whenever your intervals actually overlap, right? Being greater than 2 and less than 3 overlaps, more than likely your thing doesn't define a function. I think we'll stop there. I have a couple more things to talk about, but so 1.1 is not finished, so the homework for that is not due. But you should prepare for the quiz. There's WebAssign homework due, remember, so make sure you get your WebAssign info down.
What's the way of putting on
Teachers.
function?
Huh?
We have to put on the function?
Friday. Okay, that's it.